Wave propagation through air is the process by which sound waves travel through the air as a series of compressions and rarefactions. When a vibrating object moves forward, it compresses the air in front of it, creating a high-pressure region called a compression. When the object moves backward, it creates a low-pressure region called rarefaction. Sound waves are longitudinal waves, meaning the vibrations that make up the wave travel in the same direction as the wave. The speed of sound in air is determined by the properties of the air, not by the frequency or amplitude of the sound. Unlike electromagnetic waves, sound waves require a medium to travel through. In solids, molecules can vibrate in other directions, allowing for different types of sound waves. Which property of air decides wave speed? The speed of a sound in gases is primarily determined by the following properties. Adiabatic index, also known as the heat capacity ratio, it is the ratio of the specific heat at constant pressure to the specific heat at constant volume. For most diatomic gases like air, this value is approximately 1.4. Temperature. The speed of sound in a gas increases with temperature. Higher temperature results in faster moving molecules which can transmit sound waves more quickly. Molecular mass. The speed of sound is inversely proportional to the square root of the molecular mass of the gas. Lighter gases with lower molecular mass allow sound to travel faster. The relationship between these properties and the speed of sound in a gas is given by the formula V equal to square root of gamma RT by M, where gamma is the adiabatic index, R is the universal gas constant, T is the absolute temperature, and M is the molar mass of the gas. As an example, given that the bulk modulus B of air is 1.42 10 to the power 5 Newton per meter square and density equals 1.225 kg per meter cube, calculate the speed of sound in air. To determine the speed of sound in air, we can use the standard formula V equal to square root of B by rho, where B is the bulk modulus and rho is the density of the medium. Given that B equal to 1.42 10 to the power 5 Newton per meter square and rho equal to 1.225 kg per meter cube, speed equals square root of 1.42 10 to the power 5 divided by 1.225, which is equal to 340.49 meter per second. Therefore, the speed of sound in air is approximately 340.49 meter per second. Which property decides wave speed in solids? In a medium, two properties affect the wave speed, density and elasticity. If the density of the medium is high, the wave speed is slower and the waves travel faster through more elastic mediums. Wave speed is generally highest in solids and lowest in gas molecules because in solids, molecules are tightly packed. The speed of a wave in a solid is determined by density and Young's modulus, also known as the stiffness of the solid. Speed equals square root of y by rho, where y is Young's modulus and rho is the density. In general, waves travel fastest in solids and slowest in gases. Other factors that affect wave speed include temperature, wavelength, rigidity, and elasticity. As an example, a steel rod has a Young's modulus of 2.1 10 to the power 11 Newton per meter square and a density of 7,850 kg per meter cube. Calculate the speed of longitudinal wave traveling through the steel rod. To determine the speed of a longitudinal wave in a solid, we use the formula V equal to square root of y by rho, where y is Young's modulus and rho is the density. Given that Young's modulus equal to 2.1 10 to the power 11 and density equals 7,850, substituting the given values into the formula, we get speed equals 5,172 meter per second. Which property decides wave speed in liquids? The speed of sound wave in liquids is primarily determined by two properties. The first one is bulk modulus. This measures the liquid's resistance to compression. A higher bulk modulus means the liquid is less compressible, allowing the sound waves to travel faster through it. Second property is the density. This is the mass per unit volume of the liquid. A lower density allows sound waves to travel faster because there is less mass to move. The relationship between these properties and the speed of sound in a liquid is given by the formula speed equals square root of v by rho. This equation shows that the speed of sound increases with a higher bulk modulus and decreases with higher density. As an example, given that the bulk modulus B of water is 2.15 10 to the power 9 Newton per meter square and the density rho of the water is 1000 kg per meter cube, calculate the speed of sound in water. To determine the speed of sound in water, we can use the formula speed equals square root of B by rho, where B is bulk modulus and rho is the density. Given that B equal to 2.15 10 to the power 9 and rho equal to 1000, substitute the given values into the formula. The speed of sound in water is approximately 1465 meters per second. What is the frequency of a stretched string with tension T and both ends fixed? The frequency of a stretched string with tension T and both ends fixed can be calculated using the formula for the fundamental frequency. Fundamental frequency F equals to 1 by 2L square root of T by mu and wave speed V equal to square root of T by mu, where F is the frequency, L is the length of the string, T is the tension in the string and mu is the mass per unit length of the string. This formula is derived from the wave equation for a string under tension, where the wave speed V is given by V equals square root of T by mu. The fundamental frequency corresponds to the lowest mode of vibration, where the wavelength is twice the length of the string. As an example, a guitar string is fixed at both ends and has a length of 0.75 meters. The string is under a tension of 16 Newton and has a mass per unit length of 0.005 kg per meter. Calculate the fundamental frequency of the string. To determine the fundamental frequency of a stretched string fixed at both ends, we use the formula frequency F equal to 1 by 2L square root of T by mu. Given the values, length L equals 0.75 meters, tension T equals 60 Newton, mass per unit length mu equals 0.005 kg per meter. Substituting the given values into the formula, we get that F is approximately 73.03 Hz. What are the wave properties of a tube with both ends open? The frequency and the wavelength of a tube open at both ends are: frequency. The fundamental frequency of a tube open at both ends is F1 equal to V divided by 2L, where F is the frequency, V is the speed of sound and L is the length of the tube. Wavelength. The wavelength of the fundamental standing wave in a tube open at both ends is lambda equal to V by F equal to 2L. Here are some things to know about tubes with open or closed ends. Open ends. Air can move freely at the ends, so there is a displacement antinode at the end. The pressure in the tube is different than the displacement. Closed ends. The air cannot move, so the pressure fluctuates and there is a pressure antinode. This same location is a displacement node because the air is not moving. As an example, a tube with both ends open has a length of 1.2 meters. Calculate the fundamental frequency and the wavelength of the sound wave produced in the tube. Assume the speed of sound in air is 343 meters per second. For a tube open at both ends, the fundamental frequency, first harmonic, is given by the formula F1 equal to V divided by 2L, where F1 is the fundamental frequency, V is the speed of sound in air, and L is the length of the tube. Given the values, length of the tube equal to 1.2 meter and speed of sound in air is 343 meters per second, calculate the fundamental frequency F1 equal to 343 meters per second divided by 2 times 1.2 meters equal to 142.82 Hz. To calculate the wavelength, lambda equal to V by F1 equal to 343 meter per second divided by 142.82 hertz equal to 2.4 meters. Wave properties with one and closed tube. Wavelength lambda equal to 4 times L, where L is the length of the tube. Frequency F equal to V by lambda equal to V by 4L. Natural frequency is F equal to N times V by 4L, where N is an odd integer. Fundamental mode. The fundamental mode of a vibration is the mode with the fewest nodes in the standing wave. Pressure antinode. At a closer end, the pressure fluctuates and there is a pressure antinode. Displacement node. At a closer end, the air cannot move, so it is also a displacement node. As an example, a tube with one end closed and the other end open has a length of 1.2 meters. Calculate the fundamental frequency and the wavelength of the sound wave produced in the tube. Assume the speed of sound in air is 343 meters per second. For a tube closed at one end, open at the other, the fundamental frequency, that is first harmonic, is given by the formula F1 equal to V by 4L. Where F1 is the fundamental frequency, V is the speed of sound in air, which is given 343 meters per second, and L is the length of the tube, which is 1.2 meters. To calculate the fundamental frequency, we have F1 equal to 343 meters per second divided by 4 times 1.2 meter, which is equal to 71.46 hertz. To calculate the wavelength, we have lambda equal to 343 meter per second divided by 71.46 hertz, which is equal to 4.88 meters. In the case of a thin metal rod clamped at the center, to calculate the frequency and the wavelength of sound wave inside a thin rod clamped at the center, use the formula lambda r equal to 2 times Lr, where Lr is the length of the rod and the frequency of the sound wave inside the rod equal to Fr equal to Vr by 2 times Lr. When a rod is clamped at its center, the center point becomes a node and the ends become antinodes. The rod vibrates at its fundamental frequency when it is in this state. Analysis of progressive wave. A progressive plane wave is a type of wave that travels through a medium, transferring energy from one point to another without the medium itself not moving significantly. The general equation for a progressive plane wave traveling in the positive x direction can be written as y of x comma t equals a sine of kx minus omega t plus phi, where y of x comma t is the displacement of the wave at position x and time t. A is the amplitude of the wave, which is the maximum displacement from the equilibrium position. K is the wave number defined as 2 pi divided by lambda, where lambda is the wavelength. Omega is the angular frequency, which is defined as omega equal to pi f, where f is the frequency of the wave. Phi is the initial phase of the wave at x equal to 0 and t equal to 0. This equation describes a sinusoidal wave that propagates through space and time, maintaining a constant shape and amplitude. The wave number k and angular frequency omega are related to the speed of the wave v by the equation speed equal to omega divided by k. As an example, the equation of a plane progressive wave is given by the equation y equal to 10 sine 2 pi t minus 0.005x, where y and x are in centimeter and t is in seconds. Calculate the amplitude, frequency, wavelength and velocity of the wave. The given wave equation is y equal to 10 sine 2 pi multiplied by t minus 0.005x. Identify the amplitude. The amplitude equal to coefficient in front of the sine function, which is equal to 10 centimeter. Determine the frequency. In the general form of a wave equation is y equal to A sine of 2 pi ft minus kx. F is the frequency and k is the wave number. From the given equation, we can see that 2 pi f equal to 2 pi. Therefore, we can equate f equal to 1 Hz. Calculate the wavelength. The wave number k equal to pi lambda. From the equation, we can see that k equal to 2 pi into 0.005 per centimeter equal to 2 pi by lambda. Therefore, lambda equal to 1 upon 0.005 equal to 200 centimeters. To calculate the velocity v of wave can be calculated using the formula v equal to f into lambda. Substituting the values, we have v equal to 1 Hz, 200 centimeter equal to 200 centimeter per second equal to 2 meter per second. Having gone through the theory, we shall solve some questions of different types to make the theoretical concepts clear. Question number 1. Calculate wave velocity for a given periodic wave with a wavelength of 3 meters and that has a frequency of 6 Hz. Given that the wavelength of periodic wave equal to 3 meters and the frequency of the given periodic wave equal to 6 Hz, we have to calculate the wave velocity of the given periodic wave. From the equation of wave velocity, we have velocity equals wavelength into frequency. Substituting the corresponding values in the equation 1, we get velocity equals 18 meter per second. In the question number 2, a wave with a frequency 450 Hz is traveling at a speed of 200 meter per second. What is the wavelength of the wave? Given that the frequency of the wave equals 450 Hz, the wave velocity of a given wave equal to 200 meter per second, we have to calculate the wavelength of the given wave. From the equation of wave velocity, we have velocity equals wavelength into frequency. On rearranging the equation for the wavelength of the wave, we get wavelength equal to velocity v divided by frequency. Substituting the corresponding values in the equation 2, we get lambda equal to 200 by 450 equal to 0.44 meters. Question number 3. How much time it takes for the observer to hear the sound of explosion when the distance between them is 2 kilometers and the frequency of explosion is 100 Hz? To determine the time it takes for the observer to hear the explosion, we need to consider the speed of sound in air. The frequency of explosion, 100 Hz, does not affect the time it takes for the sound to travel the distance. The speed of sound in air is approximately 343 meters per second at room temperature. Given the distance between the explosion and the observer is 2 kilometers, that is 2000 meters, we can use the formula time equal to distance divided by speed. Plugging in the values, time equal to 2000 meters divided by 343 meters per second, which is equal to 5.83 seconds. So it will take approximately 5.83 seconds for the observer to hear the explosion. Question number 4. There are two tuning forks, A, which is unknown frequency, and B with 320 Hz frequency. When they are sounded together, 5 beats are heard in 1 second. Tuning fork A is covered with little wax and sounded again with the tuning fork B. Again 5 beats are heard in 1 second. What is the frequency of tuning fork A? Since the tuning fork A produces 5 beats per second with fork B of 320 Hz, the frequency of fork A must be either 320 Hz plus 5 Hz equal to 325 Hz or 320 minus 5 Hz equal to 315 Hz. After covering with wax, the frequency of fork A will fall down. Even after covering with wax, fork A produces the same beat sound of 5 Hz. If frequency of fork A is 325 Hz and after covering with wax, its frequency may fall to 315 Hz to produce 5 beats per second. Whereas if the frequency of fork A is 315 Hz, its frequency falls down below this value after covering with wax, and that will not produce a beat frequency of 5 Hz. Therefore, the frequency of fork A should be 325 Hz. Question 5. A string of length 20 meter and mass 2.5 kg is under tension of 200 newtons. If the transverse jerk is given at one end of the string, how long does the disturbance take to reach the other end? Mass of the string M equal to 2.5 kg, tension in the string equal to 200 newtons, length of the string equal 20 meters, mass per unit length equal to mu equal to 2.50 divided by 20 equal to 0.125 kg per meter. The velocity of the transverse wave in the string is given by the relation V equal to square root of T by mu equal to square root of 200 divided by 0.125 equal to square root of 1600 equal to 40 meter per second. Time taken by the disturbance to reach the other end equals length divided by velocity equal to L by V equal to 20 divided by 40 equal to 0.5 seconds. Question number 6. A bat emits ultrasonic sound of frequency 1000 kHz in air. If the sound meets a water surface, what is the wavelength of 1. The reflected sound, b. the transmitted sound? Given the speed of sound in air is 340 meter per second and in water 1486 meter per second. Frequency of ultrasonic sound equal to 1000 kHz equal to 10 to the power 6 Hz. Speed of sound in air equals 340 meter per second. The wavelength of the reflected sound is given by the relation lambda r equal to velocity divided by frequency equal to 340 divided by 10 to the power of 6 equal to 3.4 10 to the power of minus 4 meters. Frequency of the ultrasonic sound V equal to 1000 kHz equal to 10 to the power 6 Hz. Speed of sound in water equal to 1486 meter per second. The wavelength of the transmitted sound is given by lambda t equal to velocity divided by frequency equal to 1486 divided by 10 to the power of 6 equal to 1.486 10 to the power of minus 3 meters. It was a long session. Appreciate your interest and thank you for watching it full.